Hello. So here is a very interesting problem that we want to solve. This problem is about analog electronics consisting of one diode and couple of resistors and the voltage source. And if you specifically look at this diode, this is a special diode called as Zener diode. Okay. So we know that as we have studied from our previous model, Zener diode has variety of applications and it is primarily also used in voltage regulation application. And this question is based upon that only. So before we try to solve the problem, we want to understand what the problem statement is. So you can see that it says in the circuit shown, that means this is the circuit we are referring to, the breakdown voltage and the maximum current of the Zener diodes are 20 volt and 60 milliampere respectively. Now we know that from the Zener diode operation and its characteristics, it is an IV curve of the Zener diode. So this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So the operation of the Zener diode is primarily defined in the two quadrants, that is quadrant 1 and quadrant 4. So in the first quadrant, it works as a normal PN junction diode. So you have this exponential behavior of the current and the voltage of the Zener diode, and based on its cut-in voltage, let's call it cut-in voltage or turn-on voltage, it shows the exponential rise in current with respect to the voltage across it. So it is a PN junction characteristics that we have seen, and it is called as forward bias mode of the Zener diode. So which is also similar to the PN junction diode. Okay. However, in the reverse bias mode, when the Zener diode is reverse bias, so for example, this is a PN junction of the Zener diode, and we apply a negative polarity to the P terminal and the positive polarity to the N terminal, we say that the diode can become reverse bias. And in that situation, initially, when you apply this voltage in the reverse direction, that is a negative polarity, your current slowly increases. That is called as leakage current. And suddenly at specific voltage, where we call it as V equal to VZ, this current suddenly rises. You can see that. So rather, I would like to draw this in this fashion. There is this steady current. We can see that there is no slope in ideal situation. Okay, and this amount of current, which is a heavy current, happens at a breakdown voltage of a diode called as VZ. And that's what this voltage is defined here. So Zener diode voltage VZ is the breakdown voltage. So it is given as 20 volts. So let me write here VZ equal to 20 volts, and we'll see that. Yeah, so with the understanding about the breakdown voltage, now this is the current that is flowing, and the maximum current that can flow without making the Zener diode damaged is called as IZ. Okay, and that is the IC. This is actually IZ, but it cannot be infinitely high. You know, there is some limit, and that limit is IZ max, which is given as 60 milliampere. Now, here is the 60 milliampere. The value of this resistance is 200 ohms. Value of this load resistance is 1 kilo ohm or 1000 ohm. Now the question is, what is the range of VI that will maintain the Zener diode in the on state? So VI is to be found out. So we have to basically seek VI max and VI min. So these two values have to be. So there are four options: A, B, C, and the D. Okay, so the first option says 20 volt to 28 volt is the range of VI we should apply into the circuit to keep the Zener diode to be in the on state. Second option says we should have VI minimum to be 24 volts and VI maximum to be 36 volts to maintain the Zener diode in the on state. And when we say it is to be maintained in the on state, it means the circuit is working as a regulator. So what it exactly works so before we explain how it works as a regulator, let's have a third option, which is 18 volt to 24 volt. And the final option is 22 to 30 volts. Only one option is correct. So how this circuit will maintain the output voltage constant irrespective of the variations in the load current or the load, just say load, and irrespective of the variations in the input. Okay, so if you have the input voltage range that falls below VI min or that exceeds VI max, the circuit will come out of regulation. It is not properly maintaining that. So we have to find the optimum range. Okay, so we'll see what range is that. So how it actually maintains that, if you have a look from our previous module, so we see that I, that is the current into the circuit, I, that is equal to the current that is flowing through the Zener and the current flowing through the load, that is IZ plus IL. So how the circuit will maintain the load regulation? So first we are talking about the load regulation. So let's have a look at. So let's say your IL goes up or goes down due to some reason. You change the value of resistance or due to temperature, the RL changes and hence the IL can go up or go down. So the property of the Zener, when it is in the on state, it has this voltage drop across it indicated by VZ, which is the breakdown voltage of, let's say, right here from the curve, from the value 20 volt in the example. The VZ, if the IL goes up, the the diode will conduct the less current. Okay, look, IL is going up, so diode will conduct the less current so that I remains constant. Okay, and if the IL goes down, then IZ will be more, so diode will conduct more current, so that again the I remains constant. So this is a kind of load regulation. Similarly, you have a fluctuations in the input voltage, that is VI, goes up or goes down. So the job of the Zener diode is to maintain the constant voltage VL across the load, that is VL across the load. Okay, and that's how it will do that. So again, it will how it will do that, we'll see. VI, here we can see that there is a drop across this resistor due to the current IR. So we are applying basically the KVL, Kirchhoff's voltage law. VI minus IR minus VZ is equal to 0. So you have like VI minus VZ equal to IR, and VI minus VZ divided by R will be equal to I. So we have to understand how the voltage across the load will be maintained again if there are variations in the input. Okay. Okay, so right now we want to investigate the line regulation. Okay, so we are talking about when there are changes in the VI, there are changes into the load. We want to ensure that Zener diode will act in such a way that when there are variations in the VI, the voltage across the load will remain constant. Okay. So here we have written this equation, that is Vi minus IR minus Vz equal to 0. Vi minus Vz therefore is equal to IR. Vi minus Vz divided by R equal to R. And we also can write then Vi minus VL divided by R equal to I. So we actually can see from this equation Vz equal to VL actually. V VL equal to Vz, or yeah, because when the Zener is on, your voltage across the Zener Vz is the voltage across the load RL from the circuit diagram. So here we can write okay, VL is equal to IR, or rather let me correct it. How we can write here Vi minus VL is equal to IR, and then this equation is Vi minus IR is equal to VL. So you see now, when there is a change in Vi, there is a change in VL, okay, which we don't want. So basically we want to change this IR drop in a such a way that the VL will remain constant. So from this equation, we see if there is increment of VI, the VL is going to go up, and then voltage across this resistor R, which is the IR drop, is going to go down proportionally so that VL remains constant. So R is constant in this drop. R is constant. So I is going to go down so that the voltage drop across the resistor R is going down. Okay. In reverse fashion, if the VL goes down due to, let's say, the change in the VI, okay, so VI goes down, VL is going to go down, and then IR drop has to be up in proportion so that the VL can also be taken up as to its original value. So you see now, this is the concept of line regulation. Line regulation. Okay. So we are seeing this one by one. Okay. So that's good. But now we have to answer the question out of the four answers, which is the possible VI minimum and VI maximum right here. So obviously the Zener voltage breakdown voltage is 20 volts, as you can see here. So the VI minimum must be greater than 20 volts. So option A and option C are ruled out. We don't have these options. Only these two options are available then. I say again, because the VZ is 20 volts, so VI minimum has to be greater than 20 volt, because we just said VI minus IR minus VZ equal to 0. So VZ is VI minus this IR drop. Okay. So obviously VI has to be greater than 20. Okay, so let's start fresh. So we know the equations like VI minus VZ divided by R is equal to I, and I is equal to IZ plus IL. Here is your IL, here is your IZ, here is your I, and this is the KVL that we applied. Then voltage across here is VZ, voltage across here is VL, and obviously voltage across here is I times R. So if we see option D, for example, so let's say VI min is equal to 22 volts. So we will say 22 minus 20 divided by 200 ohms is equal to I, this equation, right? That is leading to 2 divided by 200. So it's like 1 by 100. Yeah. And then it's like 10 milliampere, 1 divided by 100. Okay, so So with I equal to 10 milliampere, we from this equation we know that IL is basically or rather we say the Zener diode when it conducts the current, the voltage across the Zener is Vz, which is equal to VL, and that would be equal to IL divided by well VL, which is equal to 20 volts, right? And then from this, IL would be VL divided by 1K. That is the resistor RL. So it will be 20 divided by 1K, which is 20 milliampere. So we know the value of I now, which is 10 milliamp. We know the value of IL, which is 20 milliamp. And from this equation, how can IZ be obtained? I minus IL. So it would be like 10 milliamp minus IL is 20 milliampere, right? So it comes out to be minus 10 milliamp, which is not true. There is a negative current. So this option is also ruled out from the first possibility itself, right? So what we'll do now, we'll explore the option B. So let's say VI min is equal to 24 volts. Therefore, I would be from this equation 24 minus 20 divided by 200 ohm, that equals to 4 by 200, that is about 20 milliampere. Okay, so now VL is 20 volts, therefore because VZ is 20 volts, right? The Zener is on, we are assuming, and then you have IL, that is 20 volts divided by 1K, which is 20 milliampere. Now IC is equal to, from this equation, you can have the I is equal to I minus IL. So I is 20 milliamp and IL is 20 milliamp. So that comes out to be 0 milliamp. So here on the characteristics curve, we just see that you are on the onset of the VZ of making the xenon that turned on with the application of 24 volts. Your Zener is on the onset of turning on. So this voltage is the minimum voltage you want. Rather, we would say greater than 24 volt, equal to or 20, greater than 24 volt. Now VI max would be, let's say, 36 volts, which is given here. So it would be then I would be 36 minus 20, which is the VZ, divided by 200 again. So it is like 16 divided by 200. That comes out to be, how much that comes out to be? 16 divided by 200. 16 divided by 200 would be 80 milliampere. So you have like, let me write 80 milliampere. That's the current. And coming back here, IZ would be I minus IL. IL is going to be the 20 milliampere that we calculated here. Okay, so it is 80 minus 20. That comes out to be 60 milliampere, which is the maximum Zener current. The current that Zener can allow to flow through it before it fails, before it gets destroyed. Okay, from the IV curve. So I said max. So that's the maximum voltage you can apply. So option B is correct with respect to our analysis. Okay. So option A, C, and D are ruled out, and option B is the correct option. So this is how this circuit will maintain the Zener diode on for the given voltage range of input voltage, that is from 24 volts to 36 volts. And when it does so, it is acting as a regulator, and it is regulating the output voltage against the variation in the load, against the variation in the input, as we've seen before. So with that said, we stop here and hope you found the video useful. If you did so, share it with others, like and subscribe, and stay tuned for more engaging contents like this. Till then, wish you happy learning.